So sound and ultrasound are both longitudinal waves. They travel as compression waves through the air. So if you've got an object that is vibrating, it will cause compression in the air around it, which will travel as sound waves. Okay, so I'm going to say that let's say this loudspeaker is vibrating. If this loudspeaker is vibrating, it will produce pressure waves in the air, and I'm going to represent pressure waves the same way as I represented them before, longitudinal waves, as compression lines. Okay, so the waves will travel, and then you'll have areas of compression. Okay, and then maybe another area of compression. Okay, and then it will travel to the device that detects it. In this case, our ear. Okay, the sound waves will then travel down the auditory canal and hit this eardrum here. Okay, so when sound waves hit any solid object or hit an object, it's going to cause that object to vibrate as well, and that's what it does to your eardrum. It will hit your eardrum and cause your eardrum to vibrate, and your eardrum will then cause these tiny little bones inside your ear called ossicles to vibrate. Okay, and then those vibrations will travel down the semicircular canals and into your cochlea. Okay, your cochlea looks a little bit like a snail in this picture, and the cochlea it takes those vibrations and transfers them to electrical signals that get transferred down your auditory nerve and then to your brain. Okay, and then your brain will detect those and pick those up and interpret those as sound waves. Okay, so that's sound. Now, sound waves, the human ear can hear sound waves between 20 hertz and 20,000 hertz or 20 kilohertz. Okay, if I had a microphone instead of an ear, a microphone works because it's got like a paper diaphragm that will vibrate when the sound waves hit them, and then those are transferred into electrical signals as well. Okay, that can be detected by whatever you've got your microphone plugged into. Microphones can pick up a much larger range, but your human hearing can only pick up 20 hertz to 20,000 hertz frequency range of sound. Now, ultrasound is any sound that is beyond 20,000 hertz. So anything that's higher than 20,000 hertz we classify as ultrasound because we can't hear it. And they can be used for a variety of applications, such as medical imaging, in this case prenatal imaging. So I've got an ultrasound scanner here, and just like any other wave, when it hits a boundary, some of it might go through, some of it might be transmitted by that boundary, some of it might be reflected, some of it might even be refracted. Okay, so every time it hits a boundary, some of it will go through, some of it will be reflected back. Okay, so in this case, the wave comes out of the detector, some of it will go through the boundary, some of it will be deflected back. And then the same thing here with the baby's head. Some of it will be reflected back, some of it will go through. Okay, and then when that gets picked up again by the receiver, the computer that it's plugged into will run it through some special software that will produce an image of whatever that thing is, so maybe a baby or something like that. Okay, so the computer software will look at that, the sound wave coming back, and it will interpret that, put it through some software, and produce an image. Okay, so it's non-invasive imaging here, so we don't have to cut people open to see inside them. We can use completely harmless ultrasound waves. Okay, we can also use them in industrial imaging. So in this case, I've got a piece of metal here. Okay, in reality, it can be any material. If you take an ultrasound scanner and you want to check for defects, such as like small little hairline cracks or something like that you can't see with the human eye, maybe there's something inside there, maybe an imperfection inside that metal that you can't see or get at without cutting it open, you can actually use an ultrasound scanner to check for those defects. And an ultrasound scanner will send the ultrasound through. Some of it will be reflected by the cracks, some of it will go through, and you can see that there's something there that you shouldn't be there. Okay, so you might want to throw that piece away, or you might want to, not use it for something that you need it, an application where you need perfect, structurally sound metal. Okay, we can also use it in applications such as echo sounding. So, for example, this submarine might want to know how far away the ocean floor is. So what they can do is send an ultrasound down to the ocean floor, will then be reflected off the ocean floor and back up here. you can time how long it takes to receive that pulse again. So it'll pulse it, and then you can time how long it takes to receive it again. And then you can use the speed of sound in that medium, in this case water, and you can then work out the distance using speed equals distance divided by time. In this case, just be aware that if you are asked to do a calculation such as this, just be aware that the sound wave is going down and then back up again. So it's there and back again. So you've got to half the time. Otherwise, you'll be getting double distances. Yeah. So it's got the sound wave goes there and back again in that time. So you've got to take that into account. Okay, that's sound and ultrasound. I will see you in the next video.